Hello, I am Álvarez-Blanco and I am going to present the work entitled Crack Morphology in Lattice-Core Specimens made of a biopolymer via fused deposition modeling. This work was developed together with Adrián Arias, Diego Infante, Miguel Marco and Eugenio from Universidad Carlos III de Madrid and Universitat Politécnica de Valencia. This slide shows the contents of the presentation. I will start with a brief introduction, following with the methodology, and finally with results and conclusions. As I said, firstly, a brief introduction about 3D printing. We selected some important advantages of the fused deposition modeling or 3D printing manufacture over other processes, like the exponential growth of interest, the possibilities of complex manufacturing, and large variety of materials and properties. As shown in the slide below, these specimens have anisotropic mechanical properties influenced by printing parameters, complex heterogeneous geometries to be studied because of the lattice-core or the nasal trajectory, for example, and they are highly dependent on the strain rate during fractures. When we talk about 3D printed specimens, we think about pieces with customizable grid patterns and outer surfaces. These specimens have similarities with sandwich composites as an inner honeycomb pattern with exterior shells, and to the interest in bending behavior and fracture patterns. Many works about it for sandwich composites are published, like the article reference on the right, but literature about fracture in printed materials is limited. There are few works that analyze crack paths in 3D printed specimens, like the article below, but that studies this subject from a global view. Therefore, it's needed the analysis of this type of specimens in detail. So, two topics that we consider very important in this research field are the analysis of fracture patterns and mechanical behavior at mesoscale, and the study of defects and their influence. So the main objective of this work is the analysis of the fracture path in PLA specimens under 3-point bending test. In order to achieve this goal, we apply the digital image correlation technique during the 3-point bending test to study the strain field before the fracture. In addition, we created numerical models based on classic fracture techniques to be compared with experimental results. In this section, I will present the biopolymer analyzed, some manufacturing characteristics, the experimental tests developed, and the corresponding numerical models. The specimens we tested were made of PLA filaments using the 3D printer Epsilon W50, and in the table below there are some of the most important printing parameters that are set by default. These are the specimens we used in this work. On the left we have the tensile sample or the dog bone sample for the tensile tests with 100% density and the dimensions you see in the design drawing. On the right, the prismatic samples for the 3-point bending tests with 100 mm length and a cross-section of 10 by 20 square millimeter. And it's important to take notice of the axes we will use during this presentation in the figure on the right. We consider the testing of specimens with no shells very important to observe the behavior of the inner pattern during the fracture, but we also created samples with shells for their comparison. To identify each specimen, we have in the table all the different designs we tested in this work. The number of outer shells and number of top and bottom layers are chosen to generate an homogeneous cover around the inner pattern. Now, the experimental tests we developed for this work. We used a universal testing machine to carry out both tests, the uniaxial and 3-point bending tests, and also in both of them the digital image correlation technique has been applied, taking pictures from two spots at a certain frequency and tracking a region of interest to analyze the deformation field during the test. On the left, we can see the uniaxial test setup, following the standards indicated below and using an extensometer to measure the strain before the fracture more accurately. We also carry out tests at 1 and 50 mm per minute to analyze the influence of the strain rate. On the right, we have the 3-point bending test setup with some important parameters. Following the standards too, like before. We wanted to analyze the specimens in two orientation because of the anisotropy of the material, as is shown in the figures below. For the corresponding numerical model, the main challenge was the modeling of the fracture evolution itself. The crack propagation has been numerically modeled by the so-called phase field fracture model, and in particular we have used a recent code implementation in Abacus by Naviterani. The nucleation and growth of cracks are described by using a smooth continuous variable, phase field, represented with a symbol phi, going from 0 to 1. Phase field variable takes the value of 0 when there is no damage and 1 at the crack phase. Because it's a continuous variable, it changes smoothly from 0 to 1. An example of the predicted crack in a simulation of 3-point bending test is shown in the figure, with the phase field variable represented in the color legend. The phase field fracture method is based on the interpretation of Griffith's criterion as a variational principle. In this slide, there are some features and parameters that need to be determined for the implementation of the phase field fracture method using a subroutine in Abaqus. The numerical model shown in the figure below corresponds with the 50% infill density specimen with no shells. To reduce the computational cost, it's a 2D model that represents the 3-point bending test with the cylindrical supports and the moving punch on top. On the right, the figure zooms in on a sample area to show the mesh of elements. A very small mesh size is necessary to apply this fracture model. Now, in the results section, we are going to analyze all the data we got from the experimental tests and numerical models. Firstly, we carry out the uniaxial tests with dog bone specimens for the mechanical characterization of the PLA, and the graphic on the left represents the force displacement curves of two tests with different strain rate. It can be noticed that while the test at 1 mm/minute reaches a stabilization zone with large deformation after the maximum force and the elastic recovery, the test at 50 mm/minute ends with a brittle fracture of the specimen when this maximum force is reached. The graphic on the right represents the curve stress strain obtained by the extensometer, validating the good results of the digital image correlation that represents also the elastic recovery in the region of interest. The evolution of the deformation field analyzed by the digital image correlation allows us to obtain the Poisson's coefficient. The table in the middle includes the mechanical properties of the PLA obtained in these experimental tests. After the mechanical characterization of the material, I am going to present the experimental results of the 3-point bending tests. This slide shows the results of the specimens with no shells and the orientation where the crack propagates over the plane XY. The force displacement curves correspond to the specimens with 30, 50 and 75% infill density, and the figures below with the samples before and after the bending. As a reminder, the test velocity was the same for all of them, 1 mm/minute. We can notice that as the infill density increases, the maximum force increases too. In the case of 30% specimen, its fracture is progressive, reaching large displacements but not a complete fracture. With the digital image correlation technique, we were able to verify that these jumps in the curve correspond to gradual breaks in each joint of the inner pattern of the crack path. In the other tests with the 50 and 75% specimens, this high plasticity does not appear. Instead, the complete fracture is abrupt and occurs after a small displacement. We continue with the experimental results of no-shell specimens, but rotated. Now, the orientation where the crack propagates is the plane XZ, and there are similarities in the results obtained before. The 30% specimen curve shows again high plasticity without a complete fracture, and now in this orientation, the 50% specimen behavior is similar to the 30%. Again, the 75% specimen experiments a brittle fracture as in the previous orientation. Now, with the same orientation, we are going to analyze the experimental results of the specimens with one shell, with the same infill densities, 30, 50 and 75%. You have a small sketch on the right to know from where the pictures have been taken, and the figure on the top is the grid pattern inside the specimens below. These figures show that these specimens experiment a planar cross-section crack parallel to the load line and starting from the tensile phase of the sample. It can be noticed that the inner pattern influences the crack path in the outer shell, following the empty spots of the grid. In order not to exceed the maximum time of the presentation, we will focus on the specimen with no shell and 50% infill density. The figure represents the orientation of the sample with respect to the supports and the moving punch, as well as the crack path from 1 to 4. Each of these numbers is a grid joint in order of fracture. It shows how the crack starts in the tensile phase at the bottom and continues to the left of the loading point to complete the fracture with a vertical propagation to the top. The results of the digital image correlation are represented below. These videos show the strain just before the fracture in the 4 joints of the crack path. The blank zones are parts of the region of interest that could not be analyzed by the code because of the noise of the pictures. In joints 1 and 2, there is much tensile strain before the fracture. Note that this high plasticity appears in a side of the joint, and we will study this failure in the next slides. By contrast, the strain in joints 3 and 4 is lower and the fracture was immediate. So the digital image correlation almost could not capture previous steps. Also, you can notice that the strain in joint 3 is the lowest because this point is on the neutral axis before the crack formation. We continue with the same specimen and bending test. These are the 4 joints studied at microscope view, and now we can analyze the fracture in detail. In figures 1 and 2, it can be observed microplasticity necks in the deposited filaments in each layer of the joint. Filaments in figure 3 are almost intact after the fracture, and the crack path in this case occurs through the middle of the joint. And the joint 4 seems the result of an abrupt fracture generating a rough surface. The microplasticity necks that we mentioned before are caused by the grid pattern. On the right, we have the video of the trajectory followed by the printer's nozzle to complete the layer. It can be observed that the filament goes through each joint twice, so in these points there is an accumulation of material. In the first figure, before the bending, it's possible to see this overlap of filaments in the joints. The following layers compact the filament in these points, reducing its diameter before the solidification. During the bending, these zones are critical for tensile stresses, generating plasticity necks until the total fracture. In the second figure, you can note how the microplasticity necks start growing from the tensile zone at the bottom of the specimen. Regarding to the numerical models, this is the crack path prediction in the no-shell 50% specimen, simulated in Abacus with the phase field implementation. As you see in the legend, red color corresponds to the value 1 of the phase field variable, or in other words, the failure of the material. Comparing the results we obtained, we can notice that the numerical crack does not correlate with the experimental one. The numerical models have no manufacturing defects. The grid pattern is a perfect repetitive geometry with no pores or design alterations. By contrast, the printed specimens have critical imperfections that could advance fracture growth and also have a strong influence to lead the crack path, like in this case. To finish this presentation, we will collect all the ideas and conclusions that we have obtained as a result of this study. After this work, we know that the crack paths are significantly influenced by FDM processes parameters. The infill density directly affects failure mechanism under 3-point bending tests. The crack path analysis and DIC technique provide important information of manufacturing defects affecting failure. And the numerical models, which do not include manufacturing defects, do not correlate with experimental crack paths. It's important to make it clear that this is a preliminary work. More experimental tests should be done and a deeper numerical analysis, as well as a further study of the printing parameters trying to minimize the manufacturing defects. Thank you so much for your attention. You have my email below, and please contact me if you have any question.